scarred, exhaust and everything. And then I mean, basically, somebody else strike out. It's just cosmetic. That if you, I guess, they're it's not great. Every morning.
Hi, everyone. Hi, everyone. Well, it is my great pleasure today to welcome Kareem El-Badry. Kareem is a sort of paleontologist of binary and multiple stars in the Milky Way, and he's going to tell us all about how he's been using Gaia data to really dig down and uncover these systems and learn all about their populations and all the different flavors that come in. Kareem was here for a while, and but is a professor at Caltech now, and before that was a postdoc here and did his PhD at Berkeley. And so without wasting any more time, let's get right to it. Thanks, Kareem.
All right. Thanks, Morgan. Thanks, everyone, for coming. It's great to see a lot of familiar faces in the audience, and I'm looking forward to telling you about a lot of work that started while I was a postdoc here and continued in the last few years. I know lots of you work on very different topics from this, so feel free to raise your hand and ask questions during the talk if you want. So I'm going to tell you about binary stars and about astrometry, that is measurement of small angles on the sky. And these two topics both have a long history, and their history is closely intertwined. So we're going to start at the beginning. In 1779, with this guy, William Herschel. So Herschel had a 6-inch telescope, and he used it to observe all kinds of astrophysical objects and made these hand drawings of them. Here you can see his drawing of a binary star with another star a little farther away. There's the same patch of sky in a modern image. And Herschel was kind of obsessed with making catalogs of different kinds of astronomical objects. And the one he spent the most time on was catalogs of double stars. So here's now images from a modern sky survey of some of the double stars that Herschel observed. These are typically sort of 7th to 10th magnitude objects, just a little bit too faint to see with the naked eye, but pretty bright. And Herschel found more than 1,000 of these and cataloged their motion over the course of a couple decades. You can see here's the first paper that he wrote about them in 1782, and they wrote a series And the interesting thing is that Herschel was not looking for binary stars. Actually, Herschel didn't even know that binaries existed. He thought all stars were single. He was looking for chance alignments of stars that are at different distances. So one star in the background, one in the foreground. And the reason he wanted to find these is that he wanted to measure stellar parallaxes, which hadn't been measured yet. That is the apparent motion of a foreground star relative to a background star as the Earth goes around the sun. And Herschel didn't have a global reference frame against which to make measurements of where the star is, so he realized it'd be a lot easier if you had another star that was in the background and stationary, then you could just measure the small angular displacements of your foreground star relative to that. And so with that in mind, he cataloged these 1,000-ish visual doubles, and then over the course of 20 years, tracked their motion and changes in their relative positions. So it's a clever idea, but if you think about it with a modern lens, you should realize that there's no way that this can actually work. And the reason is that these are almost all physically associated wide binaries. So they're at the same distance. And so you can't measure the parallax of one with respect to the other because they're both experiencing the same parallax. But what Herschel did find out is that a large fraction, something like 10% of stars, for solar-type stars, have these physically associated bound companions that separation is typically 1,000 AU. But he didn't measure parallaxes. So now we skip forward about 40 years to this guy, Friedrich Wilhelm Bessel. Bessel's most famous for his functions, which you can see here. But he actually only spent a few months of his life working on the functions. Most of his time was spent doing astrometry at this observatory. And he had this instrument called a heliometer, which is basically made for measuring small angles on the sky. Originally, it measured changes in the angular size of the sun over the course of the year as the Earth goes around its slightly elliptical orbit. And so Bessel also wanted to measure stellar parallaxes. And he focused on another binary called 61 Cygni, shown here. He chose a wide binary because he knew the two stars are the same distance, but a wide binary basically gave him twice as many measurements to make for one object. So you could measure apparent parallax of both stars and then average them to get a better measurement. Unlike Herschel, he didn't try to measure the position of one with respect to the other. Instead, he chose these reference stars A and B, which are much farther away than the separation between the two stars. And every night over the course of a year, he made these precision measurements of the distance of both of the stars in 61 Cygni to these two comparison stars. So you can see these are distances measured in hundreds of arc seconds. He tried to do it every night. Some nights it was cloudy. And so I occasionally have to stay up at night and observe, and I get grumpy if I have a few nights in a row because it messes up my sleep schedule. But whenever I get too grumpy, I'm glad that I at least don't have to do it for 365 days to try to measure distance to one star. And the thing that made it especially difficult is that actually every night he made 16 separate measurements of the same star times two, so 64 separate measurements, and then just averaged them to try to beat down the noise because he realized that the atmosphere is turbulent. Right? The unsteadiness of the atmosphere is a great obstacle for this kind of work, but you can beat down a lot of that noise just by making repeated measurements. So here's Bessel's data. This is the displacement in arc seconds to one of the reference stars as a function of time. And on top of it, I plotted a sinusoid. You can see that sinusoid is the first stellar parallax. And so Bessel measured parallax of about 0.3 arc seconds, plus or minus 0.02, which gives you a distance of 3.2 parsecs. And it was actually a pretty good measurement. So there you can see the modern distance from Gaia is about 3.5. So he was right within 1.4 sigma, which is better than most of us do today in our error bars. So that was the first measurement of stellar parallax. The other interesting thing about 61 Cygni, because it's a wide binary, Bessel could actually see that the stars are orbiting a little bit. Their position angle is changing. And that motion is small compared to the parallax, but not negligible. It's about 2/3 of a degree per year in their position angle. And so from that, he guessed that the orbital period has to be at least 540 years. And now we think it's probably about 700 years. So that was good, too. And so in this case, it made sense that the star won't be moving quite in a straight line, even after the parallax is taken away, because of orbital motion. Things got a little more confusing a few years later when Bessel kept making these kind of measurements for other stars. And so here's measurements for Sirius. This is now data taken over more than 50 years. And you see the displacement in right ascension is not a straight line. And then there's another star he looked at called Procyon. Here you see the displacement and declination for this one. And you see, again, it's not a straight line. And this is on a long period, so we're not seeing a parallax here. Right? A parallax is all within the course of 1 year. And that was confusing for Bessel, because when you look at these stars in the sky, unlike the 61 Cygni, they're not wide binaries. You don't see another star there. So he says the power motions of Procyon and Sirius are not constant, but since 1755 they've been very sensibly altered. And then he goes through a whole bunch of different hypotheses of why this could have happened, and rules out most of them, and eventually arrives at what he thinks is the most likely one. He says if we were to regard Sirius and Procyon as double stars, then the change in their motion wouldn't surprise us. But there's no companion there, but he says the existence of numberless visible stars can prove nothing against the existence of numberless invisible ones. So maybe they're invisible stars, and that's what they're orbiting. And it turns out that was exactly the right explanation. So it's good to be bold in your interpretation of the data sometimes. So here we can see now with the HST image what's going on for Sirius. You've got Sirius in the middle, big bright thing. And then off in the lower left, about 1 million times fainter than Sirius itself, is a little point of light called Sirius B. It's a white dwarf. And here you can see now a much higher precision orbit of the position vector of the Sirius A to Sirius B with HST. You can see now the measurement uncertainties are like 3 milliarcseconds, about a factor of 1,000 better than Bessel was getting. And in this case, the separation between the white dwarf and the main sequence star is about 20 AU. And so that's good for Sirius because it means probably the binary could have formed and lived out its life without much interaction between the two components. So the object that is now a white dwarf used to be a more massive star, more massive and brighter than Sirius itself. It became a red giant, lost its envelope, now it's fading. But even when it was a red giant, it was big enough that it wouldn't have run into Sirius A. And so in a sense, the formation of this system you can understand reasonably well without binary evolution. You can think of it as two stars evolving on their own. So that sets the background. We're going to talk for the rest of the talk about these other numberless invisible or almost invisible companions that make stars move not in straight lines. And most of what I'm going to talk about has been made possible by this mission Gaia. This is a little movie. So Gaia, for about 11 years, was at L2 in space, spinning around its axis with a period of 6 hours. And in doing so, its cameras sweep out an annulus on the sky. But then the precession axis, the rotation axis is precessing with a period of 63 days. And as a result, on average, every month or so, Gaia returns to each point of the sky and makes a precise measurement of where all the stars are. So the amazing thing about Gaia is that these measurements are very precise. At the bright end, they reach about 100th of a milliarcsecond in the individual epoch measurements. Bright here means brighter than about 13th magnitude. And so I want to give a little context for how small this angle is. And so one comparison point is if I'm in California and I point my telescope at Massachusetts, 100th of a milliarcsecond is the width of a human hair in Massachusetts. Some people find this impressive, but astronomers are used to crazy big or crazy small numbers, so I can understand why the reaction is a little muted. Perhaps something you can relate to better is this image, taken with the Event Horizon Telescope of the black hole in M87. This image is 0.1 milliarcseconds on the side, so it's 10 times larger than the precision with which Gaia can centroid a bright star. Of course, Gaia can't make this measurement because it's the wrong wavelength and this is fainter. But Gaia doesn't need a 747 full of hard drives to make its measurements, and it's doing them for 1 billion stars at once. So it's pretty amazing data. Another reference point is that the precision is about 10 to the 4 times better than Bessel could do with the naked eye or with a small telescope. And so Bessel could basically measure parallaxes and orbits of stars that are a few parsecs away. that means that for bright stars, Gaia can measure parallaxes and orbits at tens of kiloparsecs, which is basically the whole Milky Way. In practice, only for very luminous stars can it do that, because most stars, when you put them on the other side of the Milky Way, are too faint. But nevertheless, a significant fraction of the Milky Way we can do astrometry with Gaia for. And so if you have a binary, then every time Gaia looks at it, you get one of these little measurements. That's a displacement of the photocenter relative to a distant background. And once you get a few tens of these, you can fit an orbit. And you get something like this, which is a real orbit of a binary star. And you can do this en masse across the whole sky, basically for free, because Gaia is getting this data for almost all the stars. So I said Gaia did this for 11 years. And it was decommissioned just a couple months ago in February of this year. But nevertheless, I'm going to try to convince you today that Gaia is actually just getting started. The best science is yet to come. And so the reason for that is that Gaia has observed for 11 years. It's taken on average about 120 astrometric measurements for each source. But it turns out it takes a really long time to process this data. And so far, less than a third of the data is actually processed and available to fit astrometric orbits, only the first 3 years. And so in the next year, we're going to have another data release with about twice as much time, about 6 years. And then in 5 or 6 years, we'll have the last data release with all of the astrometry. So as far as binaries are concerned, we're really just getting warmed up. So a few years ago now, in 2022, we had Gaia DR3, which is the first data release with astrometric orbits. It came out while I was a postdoc here, and a lot of my postdoc was trying to understand this data and follow up some of the binaries. And so in DR3, we got about 170,000 astrometric orbits. You can see here's their orbital period distribution. And I'm just comparing them to the best astrometric measurement or mission before Gaia, which is Hipparcos in blue. And so Hipparcos gave us astrometric orbits for 235 binaries, compared to 170,000 with Gaia. And even if you don't just consider astrometric missions, but you consider all the orbits of binaries from radial velocity surveys that we had before Gaia, Gaia DR3 was still about a factor of 50 increase in the sheer volume of binaries. And so that means if you want to look for rare objects or you want to do population demographics, it's a good place to look. Then on the right side here, you can see the color magnitude diagram of these objects. And basically, most of these objects are solar-type stars. They're within half a solar mass to 2 solar masses. And that's basically a consequence of astrometry is more sensitive to nearby objects. But if you're too low mass, then you're too faint and you don't get precise astrometry. So the sweet spot is solar-type stars. And so just taking those orbits, we try to look for compact objects, systems like Sirius, where you have a luminous star and a dark companion, which could be a white dwarf. Found like 5,000 candidates for those. Or a neutron star, we had some tens of candidates, or a black hole. And there we had about 5 candidates from the initial data release. This is before we've done our own follow-up to validate these orbits and better constrain them and the masses of the companions. And so one of the main things I worked on at the CFA was doing RV follow-up of these systems using a bunch of small telescopes. So over the last few years, we've gotten something like 2,000 RVs for Gaia binaries. More than half of them come from this little 1.5 meter at Whipple Observatory with the trace spectrograph, where Dave Latham and his army of observers have almost every night been measuring radial velocities for us. And so you need to do this over a long period because the orbital periods are typically a few years in Gaia DR3. They're fairly bright stars, so you don't need a very big telescope, but you want RV precision. And so these are the typical numbers we aim for. Then we're also using a sort of a pretty similar instrument to trace in the south at La Silla. And then in the last couple of years, we've also experimented with APF, the automated planet finder, which is a, again, similar high-resolution spectrograph on a small telescope, but roboticized. So what do we do? You have some astrometric solution. From that astrometric solution, you can predict how the radial velocities of the star should be changing, if it's correct. So here's one example. It's one of the first objects we followed up. The astrometry says the companion is about 5 solar masses, and it should be moving by about 100 kilometers a second on an orbital period of a few months. So then we go to trace. We get our 3 radial velocities. And we plot them on top. And it doesn't look so good. I'll talk a little bit more about where these bad orbits come from later on. But long story short, when you try to fit an orbit to a billion sources, occasionally things go wrong. And so far in the published Gaia data releases, we don't have the actual epoch astrometric measurements. We just have the parameters of the fit to them. And so if you're looking at something that looks interesting and rare, you really have to go and follow it up with radial velocities to get independent confirmation of the orbit. Here's another case. Here the astrometric solution makes a prediction for how the radial velocity should be changing, but there's a fair amount of scatter. And that's just because the period has some uncertainty. It's based on astrometry that was several years before this. And so that propagates to a phase uncertainty when you observe at a particular time. So then we measure a few radial velocities, plot them on top. In this case, it looks more promising, but it's still not immediately clear if they're consistent with any one line. But then we can take the radial velocities and the astrometry and fit them simultaneously. And in that case, we get a well-constrained orbit. And here we get a well-constrained orbit with just 3 radial velocities, whereas if we just had 3 radial velocities by themselves without an astrometric solution, we wouldn't be able to constrain anything. So in the last several years, we've been following up all kinds of these compact object binaries, and I'll just talk about some of the highlights. So probably the first system we got really excited about, called Gaia BH1. This is basically a solar-type star in the nearby solar neighborhood, right in the middle of the main sequence. The astrometric orbit tells us that this star is orbiting around 1.5 AU orbit, moderately eccentric, with a period of about half a year. And the parallax tells us that it's about half a kiloparsec away, so relatively close as far as black holes are concerned. And then we do radial velocity follow-up. And in this case, the radial velocities are consistent with the prediction of the astrometric solution. And they tell us that the companion mass is about 9.3 solar masses, so about 10 times more massive than the luminous star. And it turns out that even if you throw out the astrometry entirely and you just rely on the mass function from the radial velocities, this dark object must be several times more massive than the luminous star. But when we take a spectrum, it just looks like a luminous star. So this is our first black hole from Gaia. Shortly afterward, we had another one, fairly similar, creatively named Gaia BH2. In this case, the differences are, first of all, our luminous star is now starting to go up the giant branch, a little bit more luminous, but again, about 1 solar mass. Again, moderate metallicity, close to solar, somewhat longer period, about 3.5 years, and about a 5 AU semi-major axis. And again, we get a black hole that's around 9 solar masses. This one is at 1.1 kilopar, 1.2 kiloparsecs. And so then we declared that we were done as far as black holes in DR3. We looked at all the other. We've also followed up some of the other black hole candidates that turned out to be false positives. There was something wrong with the astrometry. But then we were pleasantly surprised last year that there actually is a third black hole, IBH3. This one we didn't find in DR3 because the orbital period is really long. It's like more than 11 years. And so it's too long to get a good constraint in DR3. But while they were preparing the Gaia data for the 4th data release, which will come next year, the Gaia team discovered this object and decided it was exciting enough to publish as a pre-release object. And so what's exciting about this object, mainly it's a very massive black hole, about 33 solar masses. Again, quite close by, 0.6 kpc, period of about 11 years. And low metallicity is the key. So the metallicity is about -2.5. So I think that's one of the cool things about these black holes we find with Gaia is we see these stars that look like normal stars. They're slowly rotating. They're bright. We can get good spectra of them. And so we can measure metallicities. We can also measure detailed abundance patterns. And so just to show that, here's spectra of Gaia BH1 at solar metallicity, Gaia BH3 at metallicity -2. You can see the magnesium triplet. Obviously, the bottom one is lower metallicity because the lines are much weaker. And that's something that we really don't have for other kinds of black holes we can study. So we're getting large samples of black holes that are merging in gravitational waves. And in a decade, we'll probably have hundreds of thousands of those. But for those, we'll never know what the progenitor metallicity of any of the merging black holes are. Whereas here, we just have a few, but we have the masses, and we know what the composition of the black hole was because we can measure the composition of the companion star. So far from Gaia, we have 3 black holes. 2 at about solar metallicity and 9 solar masses. 1 low metallicity and 33 solar masses. I'm an astronomer, so I can fit a line. But it would be great to have a couple more data points on the line. And we do have evidence that there's probably scatter in this relation, even from other black holes we know in the Milky Way. But in some sense, it's not surprising to find a massive black hole at low metallicity, right? Even before we found these, the people interpreting gravitational wave events have been telling us that probably the most massive black holes are coming from low metallicity stars. And that's because we think low metallicity stars have weaker winds, and so they lose less of their envelopes during stellar evolution and can form more massive black holes. So it's a reasonable story, but it's something that we really couldn't test until now because there are just no massive stars that have metallicities anywhere near this in the Milky Way today, or even in nearby dwarf galaxies. So we're excited. It's a most massive black hole. So the first question we get is, but what if it's actually 2 black holes? And just from the Gaia data, it's hard to rule out a scenario like this, because when you're a star orbiting a massive object far away, the potential of one massive object is very similar to the potential of 2 less massive objects that are close together. But these are bright stars, and we can measure their velocities precisely. And so you can actually test this kind of scenario. And so this is work done by my student Pranav Nagarajan. You can see here's a simulation where you have a configuration like what's shown on the left panel. You predict the radial velocities, and you fit it with a Keplerian 2-body orbit. And then you look at the residuals down here. And you see in this case there's a big residual. And there's kind of 2 components to the residual. One is this short time scale wobble, or oscillation. That's basically the dipole gravitational potential of the inner black hole binary. And there's also a longer time scale modulation. And that's because an inner binary will make the outer orbit precess. So as you observe it longer, the orbit won't close anymore. And so Pranav led a program to get high precision enough data for Gaia BH1 to test that kind of model. And you can see it here. In the top panel, we have the radial velocities from the discovery paper. And then we did higher precision follow-up with the espresso spectrograph at the VLT and KPF at Keck. And we can get down to about 3 meter per second uncertainties in a reasonable exposure time. And so in the end, we got something like 50 of these 3 meter per second RVs taken over a couple orbits. You can see they're plotted here. And the punchline is we can measure the mass function to extremely high precision, but the residuals always look like Gaussian noise. Okay, so we don't have evidence for non-Keplerian motion like you'd get from a 3-body orbit if there were 2 black holes. Now, it doesn't automatically rule out 2 black holes, but we can quantify what it rules out. And so what Pranav has done here is basically fit the radial velocities with a 2-body orbit. That gives you a reduced chi-squared, which is pretty good. It's a little bit above 1 because uncertainties are often underestimated, but it's quite good. And then we can predict for different eccentricities and mass ratios and orientations of the inner binary, how good of a fit would you get if there were 2 black holes instead of 1. And basically, if the period of the inner binary is longer than about a day and a half, you'd get a larger residual than Pranav observes. If it were less than that, you wouldn't be able to rule it out. And that's just because a black hole binary with a period of less than a day and a half looks very much like a single black hole from far away. But if the inner period were less than a day and a half, it would merge in less than a Hubble time from gravitational waves. And so you'd need a very fine-tuned scenario where it has already shrunk out of detectability, but not yet merged. So this system almost certainly has one black hole in it, not 2. one of the first questions we had about these black holes is how do they form? So for Gaia BH1, the picture is something like this: moderately eccentric orbit, 1.5 AU separation between star and a black hole. So you could say, well, my first guess is the black hole used to be a massive star. And so our models tell us, probably it should have been about 40 solar masses at solar metallicity to make a 10 solar mass black hole. There's some uncertainty on that, but suppose it's a 40 solar mass star. I know how 40 solar mass stars evolve, so let's let it evolve. And what happens is that 40 solar mass stars eventually become red supergiants. They expand to radii of 5 to 10 AU, which is too big to fit inside the orbit we observe today. So there must have been some kind of interaction if it formed from this kind of binary. But of course, this is a problem anytime you have a star orbiting a black hole. And the usual answer is, well, the star formed somewhere out here. The progenitor, the compact object, expands, runs into it, and the star will spiral in what's called a common envelope event. And if you're lucky, eventually the orbital energy liberated by that in-spiral will couple to the envelope of the supergiant and eject it. And getting this to work in this kind of scenario, with this big of a mass ratio is hard because the envelope has much more mass than the star that's spiraling in. But it's not totally out of the question that you could survive a common envelope like this. The real challenge is if you survive, you're only going to eject the outer envelope if you spiral all the way in, and because it's only once the star gets pretty close to the black hole that you release a lot of orbital energy. So in a common envelope scenario, we think the orbit should be quite tight, which is what we see in black hole X-ray binaries. In this system, the challenge is that it seems to have spiraled in a little bit, and then it kind of stalled. So there are various ways you can try to get around this. One possibility lots of groups have explored is that you didn't only have 2 stars involved, but actually you had some more complicated 3 or 4 body dynamics in a cluster. And so here are kind of storylines for how you could form each of the black holes. In all cases, you have several different stars involved. You have mergers of some stars. And actually, in most of these, you still have a common envelope. If you look at the middle and left panel, you still have a common envelope partway down. The difference is just that in these models, the star undergoing the common envelope is itself a merger product. And so it has a little bit different core envelope structure, where these models say it should be easier to eject the envelope. But there's still a lot of work to be done to understand whether the predictions of these models quantitatively are consistent with the black holes we find. That being said, there is strong evidence that at least one of these objects, Gaia Black Hole 3, did form in a cluster. And that's that this object is today associated with a stellar stream. So its orbit is going in a known stream. It has the same chemistry as the other stars in the stream. And so this object almost certainly formed in a low mass cluster, something like 10 to the 3 to 10 to the 4 solar masses, smaller than a typical globular cluster. And that is exactly the environment where these n-body simulations predict you can form these kind of black hole binaries dynamically. So I think this is decent evidence that at least some of the black holes we're finding are coming from cluster dynamics. Here's a population census of the known black holes in the Milky Way and in nearby galaxies. So on the x-axis, we have orbital period. On the y-axis, we have distance. And so the objects in the upper left corner, all the red and blue ones, are X-ray binaries discovered by X-ray outbursts. And in those, you have mass transfer from a star onto a black hole. So it's not surprising that those are at short periods, because only at short periods will the star overflow its Roche lobe and transfer mass to the black hole. And down here, we have these widely separated Gaia systems. And there's actually also one solid black hole discovered from microlensing, which is not orbiting anything. It's isolated. And the y-axis is distance. And so we think probably we're not at a special place in the galaxy, which means that distance is kind of a proxy for occurrence rate. Probably the closest black holes are the most common. And so we're probably not seeing the most common black holes yet, but of all the kinds of black holes we can see, we can infer that these 3 Gaia black holes, which are the 3 closest known black holes, are more common than the kind we see in X-ray binaries, because they're closer. So if we took the Gaia black holes and put them at distances of several kiloparsec, we wouldn't be able to find them anymore, because their astrometric orbits would be too small. Whereas if we took the X-ray binaries and brought them closer, we would still see them as bright X-ray sources. So we think most black hole binaries are in these non-accreting orbits. I said they're not X-ray bright, but we decided it doesn't hurt to look. And so my student Tony Rodriguez led radio and X-ray follow-up of Gaia BH1 and Gaia BH2 with these instruments. In both cases, detected no photons, which is not that surprising given how far apart they are. Right? You expect the black hole to accrete a little bit of the star's wind, but probably not enough to be detectable. But I think the most interesting prediction from Tony's work, he forward modeled the future evolution of these binaries. And if you could observe them for a few billion years, what would happen is eventually the main sequence or lower giant stars will expand, become red giants or AGB stars, and eventually they will overflow their Roche lobes and start transferring mass to a black hole companion. And these models that Tony computed suggest that mass transfer should be stable for something like 5 million years. So there should be a period of about 5 million years where one of these wide black hole binaries will be detectable as an X-ray binary. It would be called a symbiotic X-ray binary. You have a red giant transferring mass to a black hole. So that time scale is short, right? It's only about 1,000th of the lifetime of the binaries. But on the other hand, you can see those all across the galaxy when they're having an X-ray outburst, whereas you can only detect the nearby ones with Gaia. And so based on the few that we found, we infer there should be something like 10 to the 4 or a few times 10 to the 4 of these AU scale black hole binaries in the Milky Way, which means that there should be of order 10 X-ray bright red giant plus black hole binaries. The challenge is just to find them. And so one of the things Tony has worked on is with E Rosita, we see a lot of giants that have a faint X-ray source coincident with them. And we think some of those should be the future evolution of these systems. Most of them have companions that are not black holes, and so we have yet to confirm one of them. Okay, that's what I'm going to say about the black holes. We've also followed up a lot of neutron star candidates. And so you can see here are the radial velocity curves of 21 binaries where we have a constrained orbit, again, largely from the trace follow-up. Here are their orbits. You can see there's something like 90 nights of somebody staying up to observe these binaries with trace. What to say about these? I'll emphasize two things. So first of all, forming these has the same challenges associated with forming the black hole plus luminous star binaries, and that also the progenitors of neutron stars get too big to fit inside these orbits during their evolution. But it has the added challenge that neutron stars lose a lot of mass when they form. They're not very massive. And they're born with a natal kick, which in most cases we think would unbind these kind of wide orbits. So the fact that these exist at all seems a little bit surprising. Nevertheless, I'll talk about it in a minute, we think, strong evidence that these really are neutron stars in these AU scale orbits, at least some of them. And that evidence is that we do see neutron stars that are X-ray bright orbited by red giants. So what's shown here is some data for the nearest of these symbiotic X-ray binaries, giant plus black hole, discovered by my student Pranav. So this is a system that's 2 kiloparsecs away, which is about 10 times farther than a typical distance of the neutron stars orbited by main sequence stars that we find with Gaia. So it's drawn from a volume about a factor of 100 or a few hundred times larger in terms of stellar content. But this thing is the star is overflowing its Roche lobe, and so it's only going to be X-ray bright like it is for about 10 million years. And so basically you expect to find 1,000-ish main sequence plus neutron star binaries for every one of these that you found. But we've already found a number of neutron stars that implies an occurrence rate about 100 times smaller. And so that, in this case, we really know that the companion is a neutron star because we see it in X-rays, it has outbursts, it behaves like a neutron star. And so this is exactly the system that we think these main sequence star plus neutron star candidates will evolve into. Here's the mass distribution of black holes and neutron stars that we followed up. So first of all, on the left panel, you see two objects at about 9 solar masses. One is off the chart at about 30. And then all the neutron stars are clustered between about 1.3 and 2 solar masses. So these are neutron stars that presumably have not accreted anything. Their companions are main sequence stars. But there are several that are unambiguously more massive than the Chandrasekhar limit. So if already from this sample, we can be pretty sure that neutron stars are not all born at 1.4 solar masses and only gain mass by accretion, but that there's some dispersion in their birth masses. And what it says on the slide, in between these black holes and neutron stars, there's a gap. And so if there were 5 solar mass dark objects in the sample, they would be easier to detect than 1.4, 1.5 solar mass neutron stars because they would have bigger orbits. And so we can at least, we can't rule out that those exist in some small numbers, but we can find that they're much less common than neutron stars. Here's another way to look at the mass distribution. This is now as a function of orbital period for all the neutron stars and black holes that have well-measured masses. So we've got radio pulsars, X-ray binaries, and then neutron stars and black holes from Gaia. And you see there's lots of neutron stars below 2 solar masses, lots of black holes above 5, and not much in the middle. So either these kind of low-mass black holes don't exist, or if they exist, they don't survive in these kind of binaries. Maybe because they're born with larger kicks, or because the mass transfer that precedes the formation of the binary doesn't result in the binary survival. Okay. I want to end by talking about white dwarfs. So I mentioned at the beginning we had like 5,000 white dwarf main sequence binary candidates. Here's a movie that just shows the orbits of some of these. So here the yellow star is tracing the Gaia source. Then the blue point we don't actually observe, but that traces the companion. We can infer what it's doing based on how the star is moving. And then each of the red points is a measurement made by Gaia. And so this is just a small fraction of these. These are the shortest period ones. They're more fun to watch because they go around faster. But we have a lot of these. And so I'll show that we think we can learn something about the formation of the neutron stars and black holes from these as well, but we can study their population in more detail. So first of all, what might we expect neutron stars and what might we expect white dwarf main sequence binaries to look like? So here I'll turn to population synthesis. This is a prediction from a code called Cosmic. It's one of the population synthesis codes that are widely used. So basically I generate a Milky Way full of binaries. I let them interact. Some of them merge. Some of them go through common envelope. Some of them have stable mass transfer. And at the end, I take out all the ones that have a main sequence star and a white dwarf, and I plot their orbital period against white dwarf mass. And so you can see there's lots of structure in the prediction. I won't go into too much detail, but you'll see at the bottom left, you get low mass white dwarfs formed by stable mass transfer. You get, at short periods, higher mass white dwarfs by common envelope evolution. And then at periods longer than about 1,000 days, you get systems that didn't interact at all because they were too far apart. And so they have orbits similar to what they started with. And then there's a gap around 100 to 1,000 days where you predict there shouldn't be much of anything because those systems get cleared out by common envelope. So I can then take the systems we have from Gaia and just plot them on top of this. And you can see it looks like there's some problem with the model. So it's a little bit unfair in the sense that astrometry is not sensitive to the really short periods. So we're not saying that nothing exists at short periods. But we are saying there's lots of binaries that exist in the parameter space where the model says there shouldn't be any. So there must be something that allows these binaries to interact and still stay at these wide orbits. And so my student, Natsuko Yamaguchi, has been working on these. The first thing she did is get radial velocity follow-up to confirm that the orbits are actually real. He followed up an order 100 of these. I just show some of the orbits. Long story short, the orbits are right in the vast majority of cases. Here's a plot of the masses of the white dwarfs in these objects as a function of the periastron separation. So how close do the star and white dwarf get at the closest point in their orbit? And so the objects she's done RV follow-up for the stars. And you see they all fall under this blue line, which is the maximum radius of a red giant that forms a white dwarf of this mass if it evolves without running into a companion. So you see all these objects are smaller than that line, which means the progenitor of the white dwarf should have run into the companion, and there should have been some kind of mass transfer. But they're much wider than sort of typical post-common envelope binaries that we had before Gaia, which are these red points down here that are about a factor of 100 more compact than the ones we're finding with Gaia. And so Natsuko has been modeling this population, partly using the Gaia data, and recently also using these self-lensing white dwarf main sequence binaries that we find with Kepler and TESS. And those end up being pretty useful because they're sensitive to a part of the mass ratio parameter space that Gaia is not sensitive to. So Gaia can detect any orbit, but it can't tell that the companion has to be a white dwarf unless the mass ratio is above a certain value, this dashed line. Whereas with self-lensing, you have a white dwarf that is in a binary that you're observing exactly edge on, and the white dwarf moves in front of the main sequence star, and rather than causing a dip like a transit, it causes a brightening event because it gravitationally lenses the star's light into your line of sight. And so we only have 5 of these, but we understand how they're selected pretty well. And so modeling the Gaia data and the self-lensing white dwarf, Natsuko finds that about 1% of solar-type stars have a white dwarf companion at a separation of 1 to 2 AU, which is actually a much larger number than most people would have guessed. Right? It means that something like 20% of the white dwarfs in the universe are orbiting solar-type stars. Somewhat similar to the configuration with Sirius, although this is closer separation. And they're just very hard to see until you have astrometry because they're totally outshone by the white dwarf. Okay, the last thing I want to talk about is Gaia gives us all these different kinds of interesting binaries. But if we want to learn about binary evolution and constrained models, we have to understand their selection function. And so that is a daunting task because the processing of the Gaia data is a little bit complicated. I won't go through all the details, but I'll just highlight a couple challenges. One is that several different kinds of astrometric models are fit to Gaia data, and the first one that gives an OK solution is accepted. So a lot of binaries don't get orbital solutions because an astrometric solution was OK, even if it's not very good. And then some binaries that get a OK solution but aren't good enough to pass all the tests don't get orbital solutions at all. Another challenge is that after the initial Gaia pipeline for orbital solutions is run on everything, there are these cuts that are applied in the space of parameters and their uncertainties that remove a lot of binaries that could get orbits. And so that means that, for example, if you want to know whether a binary is going to get an orbital solution, you have to be able to predict what its eccentricity error or its semi-major axis error is going to be to know if it survives all these cuts. So it's a little bit complicated. But nevertheless, Gaia is a very well understood experiment in that we know exactly where it was looking at each time. We have a very good noise model for what the uncertainties on the individual measurements were. And we can predict exactly what the orbit should look like given some underlying parameters. And so the approach that I've taken in my group in the last few years is to just try to forward model the whole experiment. So we fill a galaxy with binaries. We observe them according to the scanning law. We give them realistic noise calibrated from the residuals of well-fit orbits. And then we fit the same cascade of models that are actually fit to the Gaia data and apply the same cuts. And so here's now a plot that looks similar to the one that you saw before, except this is based on simulated data. So we get the same population of spurious orbits. We can throw out the same solutions that don't make the cuts. And at the end, we have a mock astrometric catalog that we can compare to the data. And so here you can see I'm comparing some of the properties. The agreement's not perfect, but it's surprisingly good, right? Because we haven't tuned the parameters here to try to match the data. We've just taken what we think are the most reasonable assumptions about the Milky Way's binary population. And so most of the trends you see here are just driven by the selection function, not by the underlying binary population. And so we can now then take this selection function and apply it to any hypothetical binary and say, if Gaia had observed this, would it get us astrometric orbit or not? And so you can use this for all kinds of things. I'll just highlight a couple examples. So first of all, Pranav has taken this model and applied it to 2 different models for how to form the Gaia black holes. So one is based on isolated binary evolution, and one is based on these dynamical interactions in clusters. Both of them produce a catalog of star plus black hole binaries across the whole Milky Way. So what Pranav can add then is for each one, mark Gaia observations and see which of the binaries in that simulation actually make it through all the cuts and which ones don't. And so I'll skip through some of the details. Here's the result. Isolated binary evolution predicts that in DR3, there should have been 0 Gaia black holes. And it's really 0 plus or minus 0 in that we've simulated many realizations of where you put the sun in this galaxy. The dynamical channel predicts that there should have been something like 17. And then there's some error bar based on cosmic variance, essentially. And the number observed in DR3 is 2. So we've got models that bracket the observed range and tell us they cannot have been produced by this kind of isolated binary evolution model, right? If they form by isolated binary evolution, there's something missing in the model. But the dynamical channel is predicting too many of them. We can also apply this to the white dwarfs. So here's the period distribution of all those white dwarf main sequence binaries. This is just the raw period distribution. You can see it's got quite a bit of structure in it. And from the forward model, we effectively get a completeness for each of these binaries. And so if I correct the observed period distribution for incompleteness, you can see we get something that's actually reasonably flat. This is led by Natsuko. You can see, for example, there's a sharp dip at a period of a year. That's just because the Earth is going around the sun, so you can't astrometrically characterize a binary with a period of exactly a year. That goes away when you correct for incompleteness. Also, Gaia is less sensitive to short periods, so you don't have many short periods in the data because they have smaller orbits. But when you correct for incompleteness, that goes away too. And actually, the period distribution over this range is quite flat. Right? So I think if you asked most people doing binary evolution before, they would have predicted that there should be some kind of valley at these periods because these are periods that get cleared out by common envelope evolution, but it's not there. I will say the sort of classical post-common envelope binaries, like cataclysmic variables and detached white dwarf main sequence binaries that people have studied before, those are even closer periods. They're typically periods of like a day or less, and those are off the chart. So we can't quite connect, we can't yet say what's happening in that very small region between those two populations. Okay, in the last couple of minutes, I want to talk a little bit about triples. So this is work with Kevin Burge at MIT. So this is what's shown here is a optical overlaid with X-ray image of one of the most famous black holes, V44 Cygni. So it had an outburst which led to an X-ray dust echo, you can see here. And the actual black hole is in the center of the field there. In the Pan-STARRS image, it doesn't look too remarkable, except you'll notice there's actually 2 stars that are next to each other. That's been known by people studying V44 Cygni for 50 years. But what they didn't have was astrometry for the 2 stars. And so what Kevin noticed is that if you take these stars and look at their Gaia solutions, and you imagine your Herschel, you say, yeah, 2 stars right next to each other. Maybe they have the same proper motion. The proper motions are the same. And they're so similar to such high significance, and also it turns out the radial velocities are the same, that the chance of getting 2 stars that just happen to be that close to each other by random chance is about 10 to the minus 7. And so that means that the system is actually a physically associated wide binary. But of course, V404 Sig is itself a close binary. And so we have a picture kind of like this, where we have a black hole accreting from a close companion. That's producing the X-rays. And the 3rd star is along for the ride at a separation of like 5,000 AU. So that might just seem like a curiosity. Like, who cares about the 3rd star? But it's actually important because it means that this black hole must have formed without any natal kick, or with a very weak natal kick. And the reason is just that the orbital velocity of this star at 5,000 AU is like 1 or 2 kilometers a second. And so if you kick the black hole at 5 kilometers a second even, it will lose this star. Certainly if you kick it at hundreds of kilometers a second, it will lose this tertiary star. And so this means at least some black holes must form with very weak kicks. My student Cheyenne Chariot has worked on modeling this system and others like it. And he's come up with models where the third star is actually crucial to the formation of the inner binary. And the way this works is you imagine that initially the inner binary was wider, something like 100 AU. The tertiary is still there. The good thing about this is the star can evolve and turn into a black hole without ever running into the companion. Or the companion can be at 100 AU, just along for the ride. And then only later on a time scale of millions or hundreds of millions of years does the outer star induce Kozai leadoff oscillations in the inner binary, which drive it to very high eccentricities, such that at periastron it gets close enough that tides can dissipate energy from the orbit. And so that means you can form a system like this, eventually make an X-ray binary, if you have a tertiary without having to go through a common envelope. And that's appealing because the common envelope is very uncertain for these, and it's not at all clear that the one solar mass star will ever survive a common envelope. But if you have a third star, you don't have to. And so far there's just one system, but it turns out most of the other black hole X-ray binaries we know about are too far away to have detected a tertiary if it were there. And so these tertiaries may be key to making these black hole X-ray binaries. And Cheyenne has since then done the same kind of analysis for cataclysmic variables where you have a white dwarf and a main sequence companion with ongoing accretion. And these are much more common than black hole X-ray binaries. And he found a sample of about 50 of these cataclysmic variables that have a wide companion at separations of thousands of AU. And so probably many of these form through this triple scenario where they avoid a common envelope and only start transferring mass after the white dwarf forms. OK, so I'm wrapping up. I just want to say what's next. So I mentioned at the beginning, although Gaia has stopped taking data, we still have 2 data releases coming. One next year, DR4, and then DR5 a few years down the line. It turns out for binaries, having a longer observing baseline makes all the difference. Because if you have a longer observing baseline, you can constrain binaries with longer periods. But binaries with longer periods are bigger. So you can see them, you can resolve them astrometrically at larger distances. And so that means that the effective volume of a search for binaries increases dramatically the longer you observe. And so in total numbers of binaries, you can see this is from this forward model we have. We predict something like 5 times more binaries in DR4, and another factor of a few increase from that in DR5. For black holes, we expect an even steeper increase. So we predict something like 30 black holes in DR4. And that's driven in large part by the fact that in DR3, there were all these quality cuts that turns out were sort of most pernicious for black holes. And in DR4, we'll just publish astrometric data for all sources, so we won't be subject for those. And so hopefully that correlation I had with 3 data points will look a little more impressive in a couple of years. OK, I'll end there. Just to summarize a little bit what I was talking about. Now is a good time to look for stellar mass black holes and other compact objects, especially with Gaia, but also with other ground-based surveys. Gaia stopped taking data, but we still have a majority of the data to process. And all these different populations we're finding still have key uncertainties in how they formed. And I would say most of the interesting problems in stellar physics at the end of the day have something to do with binary evolution. So both these wide black hole binaries and the close ones, and even the gravitational wave sources, we don't fully understand the information channels. All right, thanks.
Questions? I'll let Kareem call on you, but I'll shuttle this around.
Thanks, Kareem. So you showed one black hole discovered via microlensing. What's the sort of like mass range that you'll be sensitive to, or mass selection function for microlensing with Roman? And what are the like approximate numbers?
Yeah, good question. So let me see if I can find that one. Right, so this one black hole, I think the mass is something like 8 solar masses, or 7 or 8 solar masses. It turns out this is probably among the highest confidence or the highest amplitude astrometric shifts we'll ever detect for a microlensing event. So Roman is conducting a survey of the galactic bulge, and it'll detect lots of microlensing events in photometry, a smaller number with astrometry, and you need astrometry to constrain the companion mass. So I think the numbers are you expect something like 10 that are detected with high enough significance that you can measure the mass within like a factor of 3. And then a larger population, like several tens or up to 100, are detected with with more marginal significance. So it'll be less clear that it's a black hole or not. But even with 10, right, it's a different black hole population than we can see in binaries, because probably most black holes don't survive binary evolution to form black holes. Yeah, and then for the mass range, it depends a little on the relative proper motion, but it's mostly just set by the baseline of the survey. So probably anywhere up to something like 50 solar masses, you should be able to resolve most of the event.
Hi, thank you. I understand the appeal of the black hole and the neutron star, but there's historically been a lot of interest in very wide separation binaries of ordinary stars. Is that story also getting revised with Gaia?
So we do have a huge number of resolved wide binaries with just K dwarfs in them, something like more than 1 million of them within a kiloparsec. So we can study all of their distributions pretty well. We know the mass ratio distribution, the separation distribution, things like that. I think there are definitely open, interesting questions. So one question that I worked on a few years ago but isn't resolved yet is it turns out even among these really widely separated binaries, there's an overabundance of equal mass pairs of twins. Another thing that people have been able to measure is the eccentricity distribution of those. It turns out they're mostly superthermal eccentricities, which are kind of hard to form through simple arguments. Historically, much of the interest in those was to test dark matter models because wide binaries are easily disrupted by primordial black holes. You can repeat that exercise, but we're now at a level where inference is kind of limited by your assumptions about what the initial separation distribution was. People used to just assume it's a power law, and then dark matter leads to some break in the power law, but probably it's not exactly a power law in detail. Yeah, though there's updates I know about on that.
We're here. I had a question about the dynamical channel over predicting the number of black hole binaries and Gaia DR3. So how much does the assumption on the distribution of compactness in clusters of stars affect this, and can it be kind of revised to match the observed if the clusters were more puffy, basically?
Yeah, good question. So this model assumed some mass distribution of clusters. I forget exactly what it was, but I think it was, roughly observationally motivated, but somewhat curtailed by the fact that it's easier to simulate low mass clusters, so they have more of those. And both the number and typical separation of the binaries you get depends quite a bit on the cluster properties. So you definitely could assume a different cluster mass function and decrease this number. But I think that the cluster mass function is only one of the uncertainties and probably not the most important uncertainty in this. The biggest uncertainty actually is just what binary population you put in to begin with. So maybe in the future you guys will observe some radial velocities of stars and clusters and tell us what to put in.
One more question before we finish up? All right, let's thank Kareem.